Okay folks, here's the last part to Chapter 17, Molecular Shape, and this is the key to everything. This is how you do shape. This is exercise 17D, shapes of molecules. Okay, remember, the Lewis-dot structure is not the shape. All it tells you is where the electrons are found around all the atoms. Your job is to figure out, based on the geometry of how things arrange themselves, knowing about VSEPR theory, valence, shell, electron pair, repulsion. So valence shell or outer shell electrons pair up. So the outer shell electron pairs repulse each other. Electron pair repulsion is everything. The Lewis-dot structure determines the geometry or the arrangement. Okay? And then the bonding pairs, which means the atoms attached to them, and the lone pairs determine the shape. It's a procedure, and it's just something that you have to practice up to be good at, but once you understand the procedure and can visualize things, it gets pretty straightforward. So, to find molecular shape, here's your job. First, draw the Lewis-dot structure. Once you draw the Lewis-dot structure, you have to count the number of places where electrons are found around the central atom. Okay? The locations of the electrons. Single, double, triple bonds, or lone pairs on the center atom, each count as one place. Okay, remember we're dealing with electron pair repulsion. So think of a, let's see, I guess I'll write this right here. A single bond a double bond, a triple bond, and a lone pair. Okay, this is one place, one place, one place, and one place. They all equal one place, okay? But the strength of repulsion, I'll write this over here, but the strength of repulsion goes weak down to strong. Okay, so a single bond is the weakest, and a lone pair is the strongest. So all you want to do is think of each of these as a stronger and stronger and stronger magnet that wants to repel all the other magnets that are close. But they still only count as one magnet, one place where electrons are found. Okay? Important to remember that. Okay, so we found the Lewis-dot structure, then we counted up those number of places. Okay, if there are two places around a central atom, and there's the central atom, here's one place where you can find electrons, here's another. And it doesn't matter if it's a lone pair, or a triple bond, or a double bond, or a single bond, this is just a place. Okay, these two things will spread out as far as possible. That's what we get with the geometry or the arrangement. They spread out because they don't like being close to each other. And of course that's 180 degrees apart, that angle, and we call that linear. Okay, and it's two-dimensional, 2D. You can draw it right on this sheet of paper. If there are three places around that central atom, there's the central atom. You might find electrons here, here, and here. You can count them up. Maybe this is a double bond. Could be. Doesn't matter. It's just 1, 2, 3 places. Each of these angles is 120 degrees. It's flat. It's two-dimensional. We call this trigonal planar. Okay, triangular planar, like a propeller. Plane propeller. Okay. Right there's a plane. Okay, biplane. So that looks like the propeller of a plane. So it's in the same plane. It's two-dimensional. And then the last 4 places around a central atom is called a tetrahedral arrangement. Hedral means triangular face, and there are 4 triangular faces. There's 1, there's 2, behind is 3, and then underneath is 4. Each of these angles is equal if they're all 109.5 degrees, and this is 3-dimensional. I wonder if I can do this. I'll show this in my class. We'll go sideways. Okay, there's a triangle. Okay, maybe like that. Okay, there's like a tripod. So my palm is the center atom. Okay, there's 1, 2, 3 places where you can find an electron pair, and here is the 4th. And boy, that just does not work. Does that work? You can't see it. It's really tough to do in this camera way. The important thing to remember is 4 things around the central atom is 3-dimensional. This is a pyramid part, and then there's something up above it. Okay? So, we call this a tetrahedral. And you have to be able to visualize this. These are going into the board or into the paper. It's like away. This X is coming out at you, and the C and this X are all in the same plane of the paper. It's tough, I know, but if you can visualize this 3-dimensional, that's great. It will really help. Okay, so Lewis dot structure. Count the number of places, because that determines the geometry. 2 places is linear, 3 places is trigonal planar, 4 places is tetrahedral. Now, that's the arrangement. Now we have to figure out what the shape is. And remember, atoms you can see, but lone pairs are invisible. They're also extra repulsive. Remember, they were the strongest magnet, but they're invisible. So to determine the shape, this is what we do. If there are no lone pairs on the center atom, then the arrangement and the shape are the same. That's simple, right? Because all the atoms are there. It's nothing but atoms. But if there are lone pairs on the center atom, then you have to visualize what the shape is going to be. And this is the way we do it. Every time there's 2 places where you can find electrons. Okay? So central atom, one of them is an atom that's attached, and the other one is this lone pair that's attached. Okay? Well, guess what? You can't see the lone pair, so it's sort of there, but you can barely see it. Okay? Because it's not really there. It's there, but you can't see it. It's invisible, just like the force of a magnet is invisible, and yet if you stick 2 poles of the same magnet together, they repel each other. Same thing. Well, that's still linear, atom, atom, right? So 2 places is always linear, but let's look about 3 places. If they're all 3 atoms, like over here, okay, atom, 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 it's trigonal planar shape as well. What if we have one of these is a lone pair? That's there, okay, you just can't see it. So if you can't see it, what's it look like? It looks like that. And what's that shape? That shape is a bent shape. It's certainly not linear. It's bent. Okay? So 3 places can either be trigonal planar or bent. Alright? Now let's look at 4 places. There's 2 possibilities here. If you have all 4 atoms attached, then it's a tetrahedral shape as well. No lone pairs on the central atom. The arrangement and the shape are the same. But what do we have if we have 1 lone pair? If it's 1 lone pair, okay, and 3 atoms, then that's a triangular pyramid at the bottom, right? That's there. You just can't see it. So what do you see? 2 atoms back, 1 atom front. It's 3-dimensional. I guess this is also 2D, 2D. This is 3-dimensional. And it's called a pyramid shape, right? It's that tripod. Tripod. Okay. And then what's our last possible? 2 lone pairs. Because 2 things, 3 things, 4 things. There's still 4 places where you can find electrons. Okay? But because the lone pairs, you can't see them even though they're there, all that's left is that bent shape again. Okay? So, I think the easiest way to do this is to go back to all those Lewis dot structures that we did before, and we go through our business of trying to determine the shape of them. Okay, so we already figured out BR2, and clearly that's 2 things, so that's going to be linear no matter what. Distance between 2 things is a straight line. So when we're determining the shape of H2S, that's the Lewis dot structure, okay, and it looks like a line, doesn't it? I'm telling you, you better be careful with that, because how many places do you find electrons around that central atom? 1, 2, 3, 4. So there's 4 places. Okay, 4 places with electrons. So what do we say if there's 4 places? That means it's tetrahedral. Okay, it's a tetrahedral arrangement or geometry. Now, are there lone pairs? Yes, there are lone pairs. 2 of these are lone pairs, and they can't be seen. So what does that look like? It looks like this. You ready? There's a lone pair. There's a lone pair. We've got a hydrogen coming out at us. And we've got a hydrogen over here. That's a tetrahedral arrangement, but we can't see these 2 sulfurs, so what's the shape that's left? It's not linear. It's a bent shape. Okay? The only way you know that that's a bent shape is if you count up the 4 things and realize it's a tetrahedral geometry. That's the key. Okay? Let's try another one. Here's another molecule. Look at that central atom. How many places do you see electrons around that central atom? 4 places. So that means tetrahedral arrangement or geometry. Right? That's how the electron pairs spread out as far as possible without getting too close. Okay? Because they repulse each other. Okay? Any lone pairs on the central atom, which in this case is a carbon? No. So therefore, it's a tetrahedral shape. It arranges itself four things in a tetrahedral shape, just like this one, except that's a carbon, and there's a fluorine, 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 and you can see those all. Nothing disappears, nothing is invisible, and so it's a tetrahedral shape, the same as the arrangement. You see how many tetrahedrals we have here? This shape and this shape have to be exactly the same. Why? Because we've got four things, again, three atoms, or three bonding pairs, okay, and one lone pair. So if it's four things, it's a tetrahedral arrangement. Tetrahedral arrangement. Okay, so if it's a tetrahedral arrangement, that's great. So we've got a P, there's your lone pair, hydrogen, hydrogen coming out at you, and a hydrogen coming out at you. So what's the shape? That's that pyramid, right? Pyramid shape. Alright? Same thing here, because this looks exactly the same, right? One lone pair, three atoms, four places. It's going to be exactly the same. Exactly the same. Now let's try this one. How many places can you find electrons around this center sulfur? In fact, let's redraw that one. So we've got S, O, and O. We could also have drawn this as S, O, and O. Okay? Can you see that if this is exactly the same as this? 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. It's exactly the same. So how could this and this be different whenever it's exactly the same electron environment around all the different atoms? Okay? And the answer is it's not, because Lewis dot structure doesn't tell you what shape is. Lewis dot structure tells you how many places there are around the central sulfur. And that's the key. How many? There's one place where you can find electrons. There's one place where you can find electrons. And how many places is that? How many places is that where you can find electrons? Double bond equals one place. So that's the third. Okay? Same thing here. 1, 2, 3. So 3 places. What do we say about 3 places? That's trigonal planar arrangement. That's how 3 things arrange themselves to be as spread out as far as possible. It basically looks like this. One sulfur, the other oxygen, and there's the lone pair. So, if that's how they arrange itself, like the spokes on a wheel or the propellers on a plane, we can't see the lone pair. If we can't see the lone pair, what's that shape? It's not straight. It's bent shape. Okay? This is visualizing. This is knowing how to draw this in your head or on the paper. Is there any difference between this one and the nitrate ion? Let's take a look at the nitrate ion. Compare the two. Well, yes and no. There's definitely some difference. For instance, let's count up the number of places around this central nitrogen. There's 1, that single bond. There's 2, that other single bond. And that's 3, that double bond. 3 places, okay, 3 places. Therefore, trigonal planar geometry. Right? And trigonal planar geometry basically looks like N, O, O, O. Are there any lone pairs? No, no lone pairs. If there are no lone pairs, then it's trigonal planar shape. Okay? That's what the shape looks like. That's what we call it, trigonal planar. Okay, one last one. 1, 2, 3, 4. 4 things. It's 4 things around the central atom. It's tetrahedral arrangement. No lone pairs. So, tetrahedral shape. Okay guys, the more comfortable you are with this on your own, the better off you're going to be, not only in Chem 115 after you take and do well in the Chem 110B final exam, but in Chem 116 and organic if you go to see that too. Okay, have at it. Good luck. That's 17D.